Yes, Kritika.
Excuse me, ma'am.
Yes.
Ma'am, at 3:20 we have a quality meeting today.
Yes, we have.
Okay, ma'am.
Forget to attend the meeting, all of you. Okay, last class where we stopped? What we are discussing about last class? Let them join. I'll start with. Last class we started instrumentation, right? Able to see the screen?
Yes, ma'am,
Yes.
visible.
Okay. Last class we just started this instrumentation and we completed 3 experiments, correct? Potentiometry is also done. We discussed or not? Hmm? Analyzing the compounds using instrument. We just started with the colorimeter, determination of copper using colorimeter instrument, and conductometer, determination of conductance of ions using conductometer, and colorimeter works on the principle of based on Beer's law and Lambert's law, and conductometer based on Ohm's law, and potentiometer is depends on it is your applications means 3 applications are there here. Conductometer, you have to any 2 applications you have to write in the exam, like in IAR if they ask. If they don't ask anything, you have to explain all these 3 applications: strong acid versus strong base, weak acid versus strong base, mixture of acids versus strong base. These are the 3 applications in conductometry experiment. Okay, so the next is potentiometry, also we discussed. Potentiometry is depends on Nernst equation. It is worked on the basis based on Nernst equation. Nernst equation is equal to E naught plus RT by LF ln molar concentration of Mn to Mn plus, correct? Based on this principle, based on this equation, Nernst equation is been potentiometry we are going to do. the experiment. What is potentiometric experiment? Potentiometric experiment, we are measuring the potential developed in metal ionic solution. So what and all we require for potentiometric experiment? We require this indicator electrode, a platinum electrode, a reference electrode, a calomel electrode we use as a reference electrode, and a stirrer or to stir continuously stirring for helps in mixing the solutions, and we need a stall bridge and a potentiometer for connection, correct? So when you may fix all these things in an instrument, and from the burette you are taking strong potassium dichromate, strong acid in the potassium dichromate as a strong oxidizing agent in the burette, and in the beaker you are taking the whose potential has to be measured. That solution you are taking in the beaker. You are you are immersing the two electrodes and connecting these two electrodes to the instrument, and from frequently upon keep on adding of potassium dichromate from the burette to the beaker, it starts giving the value, it will start increasing the potential in the potential. So once it reaches the maximum potential, you can plot the graph. Here you can see the graph here. So usually we take FAS 25 ml FAS in the beaker and add one test tube of H2SO4. This experiment you have done in the practical also, right? So once you have added potassium dichromate, 0 ml, as soon as you take this FAS and H2SO4, immerse the electrode which displays the potential and plot in the graph. So V1 in the x-axis, volume of any potassium dichromate in the x-axis, and del E by del V in the y-axis. So once you plot the graph here, you can see, once you plot the graph here, x-axis, once you plot the graph, you will get the points like this. You'll get the points, and next when you join the points, all these points, you'll get a sudden increase here like this, inverted U shape, and this is the equivalence point where exactly the oxidizing agent, and you will get a maximum potential here, that is a maximum jump. Tabulate all the values and draw the graph del E versus del V and volume of potassium dichromate added to the beaker. You will get the graphic. From the graph you can determine what is the volume, that is volume consumed, how much volume is consumed to get the maximum potential, and calculate what is the potential developed. This is how potentiometric experiment is been done. Okay. So where and all we use this potentiometric experiment? Potentiometric experiment we use in the to determine the potential of redox titration, usually reducing agent and oxidizing agent. We use FAS versus potassium dichromate. That experiment we use this potentiometer to determine the potential. Next is construction, working and applications of flame photometer and atomic AAS, means atomic absorption spectroscopy, and flame photometer. So we'll see what is this flame photometer. You have done in your PU one experiment, right? Take the salt in the spatula and add HCl uh, and keep it in the flame. You will get different color of flames, right? This you have done in your PUC plus 2 level. Do you remember? Apple green color flame, red, crimson red, hmm? Stanchium. You have done or not? Manasa? Kavya? Kavya M? Kritika, Arpita.
Yes, ma'am.
Yes, what I'm asking something, right? You have done that experiment or not? Any compound you have
Yes,
taken
ma'am.
in the
Done, ma'am.
spatula and added HCl, and you will keep it, if you keep it in the flame, it gives different color, correct?
Yes, ma'am.
Yes. So you might have observed apple green color and blue color, strontium brick red color, crimson red color you used to get when you keep it in the flame, correct? So through observation, you can see the compound gives different color. So to measure the intensity of that particular color, we use this flame photometer to measure the intensity of the colored flame. For example, sodium, if you take sodium at 580 nanometer wavelength, it gives yellow color. It gives yellow color. And potassium at 766 nanometer, it gives violet color. Barium at 554 nanometer, it gives lime green color. Calcium at 622 nanometer, it gives orange color. Lithium at 670 nanometer, it gives red color. This is the at different wavelength, the elements emits this color. It gives its color at this particular wavelength. So in today's experiment, this flame photometer, what is this flame photometer? It is a photoelectric flame photometry. Photoelectric flame photometry. It is a branch of atomic emission spectroscopy. It is one branch comes under this atomic emission spectroscopy chapter, used for inorganic chemical analysis for determining the concentration of certain metal ions such as sodium, potassium, lithium, calcium, and cesium. So you want to measure, if you look at the flame, you can easily say this particular element gives some color. But if you want to measure its intensity based on the concentration, you use this flame photometry. It is works on the principle of atomic emission at an atomic level. So when the atoms at return to the ground state, for example, so atoms when you heat these atoms from this state, it excites to the excite get excited to the higher energy level, while returning back these atoms to the ground state. When returning back the same atom to the ground state, they emit certain energy light radiations at a visible region. At this visible region, when at a higher heat energy, at high temperature, it emits certain it emits certain light radiations, or we call it as certain radiations at visible region it emits. Due to this, during this returning of this atom to the ground state, when it is emitting certain radiations, that energy it is at a particular wavelength, you can see that color. At a particular wavelength, you can see that color. So this emits, and this wavelength that it catches by the instrument, which is flame photometer. I'll explain you what is this instrumentation. See here here you have to prepare a certain solution in the standard volumetric flask at different concentration. You have to prepare a series. First one has less concentration. Second one, standard flask with more concentration. Compared to the first one, it is less. It is second one has a little more concentrated solution. Like that, you have to prepare from 0 to zero point 0.5 or uh, zero point 0.2 normal solutions in the standard flask. take that standard flask. This is called as aerosol. This is the aspiration. Aerosol means it is a mixture of both solution, and it contains atoms in this molecule. So when it undergoes vaporization, these vapors, when it is passed to the flame, when such concentrated solution vapors, when it is reaches to the flame, these vapors atoms are molecules. It contains a molecules like this. N. It is a collide. It is together. It is joined in nature. When these molecules are in the vaporized state, in the vaporization state, and when it get heated, and this gets splits into two. One in the ground state, and the other one atom get excited to the excitation state. Okay, so when this returning to the due to thermal dissociation, these atoms get splits, and one get to the excited state, and the other another one go to the ground state. During this returning thermal dissociation, returning to the ground state, and it emits certain light radiations. When it is back to the this energy, this excited state molecule, when returning to the ground state, it emits certain light radiations. So these light radiations, it is measured at a particular wavelength, and these light radiations depends on the color. See, if you prepare the potassium solution, it gives violet color. If you prepare lithium solution, it gives red color. If you prepare calcium solution, it gives orange color. If you prepare sodium, it gives yellow color. If you prepare barium, it gives lime green color or a apple green color. Due to different wavelength, at a different wavelength, it gives different colors. So this is the basic principle behind flame photometry. Flame photometry is based on atomic emission spectroscopy. I'll show you the instrumentation once again. So procedure means in your syllabus you have determine the intensity of sodium flame at a different. For that, what you have to do, you have to prepare a different series of 246 normalities, 246 8 10 ml of standard sodium chloride in solutions you have to prepare. Accurately, you have to take around 1.271 grams of sodium chloride into 1 liter standard volumetric flask. Dissolve these crystals and make up to the mark, and prepare 1 ppm into 50 ml standard flask. Take 50 ml standard flask of different solutions, 50 ml standard flask. In that you have to take this standard flask in 2468 volume and make up to the mark with using distilled water and prepare. So this is how you are preparing different sodium chloride solutions. After preparing this and making up with the distilled water and suction using a capillary instrument, what you have to do is and place these standard solutions into the capillary and set the instrument to read the flame emission intensity at 598 nanometers. At 598 nanometer, what it happens at this capillary instrument? See, this is the instrument. After preparing a series of solutions, after preparing series of solution, you have to keep this solution here in the capillary. At this place you have to keep the solution. Once you keep the solution at this place, due to capillary action from this capillary, it sucks the solution, and when it will start heating and it converts into vapors, and these vapors reaches to the flame. Once the flame reaches catches all these vapors of solution, and it gives certain color. This flame gives certain color. So this color, with the help of all these light radiations, passes through the filter, and the detector detects the signal of that particular solution and displays in the instrument. This is for the first solution. Like that, you have to take the second solution and keep it here in the same place, and with the capillary action it sucks the solution and it get heated and converts into vapor, and these vapors catches by the flame and detector will detect the solution. Like that, you will get a points here when you plot the graph whatever the displays here, absorbance of the flame and NaCl's volume of NaCl solution, how much you have prepared. And next, plot the graph. When you plot the graph, you will get the points in a straight line. For the unknown solution, you take here and plot it. You will get the volume consumed and volume detected. What is the amount of concentrated, that is the amount of sodium chloride dissolved in unknown sample, unknown test sample. So this is how flame photometry works based on the colored flames, based on colored flames. What are its applications? If you look at the applications, flame photometer, it is used for the comparison of spectral emission of wavelength. The different wavelength standards can also be detected, and it is used to determine the concentration. It is used to determine concentration of the group of first A and second A elements, first group radicals and second A group radical elements. It is used to determine the concentration. It is used to analyze this concentration, and it is used to concentration of calcium and the hard water. If you want to measure the hard water calcium deposition, you can use this flame photometer. And also it is used to determine the concentration of sodium potassium in the urine. It is used to determine flame photometer. And flame photometer is used in the determination of calcium and other elements in biogas and ceramic materials. Biogas and ceramic materials. So these are all where we can use this flame photometer for the determination and for the analysis of different periodic group radicals and different hard water analysis, potassium, and everywhere you can use this flame photometer in the detection. And the next is atomic absorption spectroscopy. Atomic absorption spectroscopy is the instrument. It is also like flame photometry, but here it will not emit the light radiations. Here we are determining in the atomic level what is the atomic absorption spectrum, the amount, how much amount is present, amount of light absorbed, amount of light absorbed. It is determined because, and it is equal to the proportional to the concentration of the element, and how much concentrated solution you have prepared, how much light is absorbed by the instrument, that we are measuring. It will not emit any light radiations here. Here you are measuring only the at the atomic level how much it is detecting. So if you look at the instrumentation, it requires a radiation source, it requires a focusing lenses, it requires atomizer, and requires a sample holder. This is a sample holder. And next it requires focusing lens, wavelength selector, where you can measure, you can select the wavelength to absorb where exactly at a particular wavelength it absorbing. And you need a detector, you need an amplifier for converting, and you need a signal processor for whatever the signal it is been detected. It helps in processing those signals and converting into other form. One second. So this is the instrumentation. These are the instrumentation parts you require for the atomic absorption spectrum. The apparatus which consists of a radiant source, atomizer, light sources, halocathode lamp, monochromator, lenses, slits, and the detector you require. So what is radiant source? Radiant source is generally we use hydrogen lamp. We use hydrogen lamp as a radiant source at a continuous source radiation. Atomizer usually burns. It is a burners. They are burners to break the liquid sample droplets which are then allowed to enter the which are used to break the liquid samples and enter into the flame. It converts. They are burners which burns the solution. And halo cathode lamp is the emit sharp line spectra which is from the it is a cathode light source which helps in detecting these cathode whatever the atoms are present in this sample. It helps in detecting. And monochromators are the wavelength selectors means if you prepare different solutions at different wavelength you can measure that wavelength selector we require. They are monochromator. Generally monochromators are graters or prisms we use. Graters are prisms we use as a monochromator. And we require filters or slits. Filters and slits help in isolation and require spectral light elements in the line span. Detectors are usually detects the emitted light or absorbed light or a photo multipliers. Whatever the sample containing, the detectors helps in detecting those signals and helps the instrument convert in the form of a signal. So this is how the detectors helps in the detecting the signals or What time I left the meeting? Completely, you could able to listen atomic absorption spectroscopy. Pushkar? Answer attendance call. 64,
Present, ma'am.
65,
Present, ma'am.
66, 67,
Present, ma'am.
68,
Present, ma'am.
69,
Present, ma'am.
70, 71,
Present, ma'am.
72,
Present.
73, 74, 75, 76,
Present, ma'am.
77,
Present, ma'am.
78,
Present, ma'am.
79,
Present, ma'am.
80, 81, 82,
Present, ma'am.
83,
Present, ma'am.
84,
Present, ma'am.
85, 85, 86,
Present, ma'am.
87, 87, 88, 89,
Present, ma'am.
89, 90,
Present, ma'am.
91,
Present, ma'am.
92,
Present, ma'am.
93, 94, 95, 96,
Present, ma'am.
97,
Present, ma'am.
98, 99,
Present, ma'am.
100,
Present, ma'am.
101, 102,
Present, ma'am.
103, 104, 105,
Present, ma'am.
106,
Present, ma'am.
107,
Present, ma'am.
108,
Present, ma'am.
109, 110,
Present, ma'am.
111, 112,
Present, ma'am.
113, 114,
Present, ma'am.
115,
Present, ma'am.
116,
Hello? Ma'am, 113
117,
present.
117, 118,
Present, ma'am.
119,
Present, ma'am.
120,
Present, ma'am.
121,
Present, ma'am.
122, 122, 123. Okay, what was the last topic you have seen before I left? Huh? Atomic absorption spectroscopy, you were there? All of you?
Yes, ma'am.
Completely?
Yes, ma'am.
Okay, okay. Now then, nanotechnology will start from the next class. Okay. Okay, all of you attend the meeting at 3:20 sharp. 3:20, right? Today? Without fail,
Yes, ma'am, at 3:20.
everyone should attend that meeting. And whenever I call the names to give to tell something about teachers,